Good evening, ladies and gentlemen. The two famous names in the history of radio astronomy are Carl Jansky and Grote Reber. As you know, Jansky discovered extraterrestrial radio waves, and Reber took the discovery, which was then a curiosity, and turned it into a very prolific and exciting science for which many of us are very grateful. Tonight, we're going to have the Carl Jansky lecture given by Grote Reber, which I think is very appropriate. I think I can hardly say anything more than that. Grote Reber, you're going to see, is a tremendously imaginative, energetic person with great curiosity and independence. These attributes have led him to pioneer in a variety of fields, including radio astronomy. For example, he has studied the carbon dating of aboriginal campsites in Australia. He has studied the twining of plants around poles, whether they go clockwise or counterclockwise in the northern and southern hemispheres. In the process of the latter, he became the world's greatest bean grower in Greenbank, West Virginia. But tonight he's going to tell us about his early days in Wheaton, Illinois. I'm sure it's going to be most interesting. He is a truly free and independent spirit, a vanishing breed today. I'm very proud and honored to introduce you to Grote Reber. Let me get this on you, Grote.
Okay. Can everyone hear me now? I hope so. Well, as the chairman said, I'm to talk about radio astronomy in Wheaton, Illinois. And when I was approached to give this lecture, this was one of the requirements. And it's an old adage that the man that pays the piper has got a right to call a tune. So I will talk about radio astronomy in Wheaton, Illinois. But before I do, I think I won't talk about beans. In any case, I like to talk about some of the general aspects of astronomy and electromagnetic waves. Now, I think most people here are aware that the sun is a star, and it's simply so bright because we're so close, and that most of the stars that are visible at night have a luminosity equal to or greater than the sun, but they appear faint simply because they're so far away. Now, the sun and all the rest of the stars that we can see with the unaided eye are part of a great aggregation of stars known as the Milky Way. This aggregation is in the form of a flat disk, similar to my watch, and we're about halfway between the front and the back face and far off center, like about maybe the center of the second hand, maybe farther out than that. So if we look down or if we look up, we're looking through a region where there are not very many stars in the line of sight, and so the sky appears black. But if we look off in the direction of the plane of the watch or the Milky Way, we're looking in directions where there are very many stars in the line of sight, and the eye is unable to resolve these separately. It just adds up or integrates the light from these unresolved stars and creates a luminous glow over the sky. Well, now, this has aspects both as far as light waves are concerned and as far as radio waves are concerned, which I will discuss briefly. Now, the nature of light has attracted people since time immemorial. And during the 17th century, there were two people, Newton in England and Huygens in Holland, who put forward different views as to the nature of light. Newton espoused the proposition that light consisted of some kind of little particles or corpuscles, as he called them. Presumably these came out of all incandescent objects and bounced around the environs and ultimately went through the pupil of the eye and impinged on the retina, creating the sensation of sight. Huygens had the idea that light consisted of waves. Neither of these could be called a theory. They were a little better than an idea, probably better called a speculation. Now, during the 18th and the first half of the 19th century, a vast number of experiments were made upon the nature of light. This is what it consisted of, how it worked, and what it was. And it became clear that whatever else light might be, it certainly had a wave connected with it. So the wave theory of light gained strength, and it was put on a solid mathematical foundation by Clerk Maxwell a little over 100 years ago. And this became known as the electromagnetic theory of light. Now, I will try to give a mechanistic explanation of the electromagnetic theory of light. It will not satisfy the purists, and they'll have to come back another day. Now, as the name implies, there is an electric lines of force, or vectors, like my fingers of my left hand. And there are magnetic lines of force, or vectors, like the fingers of my right hand. And they're crossed like this at 90 degrees. And this wave will come up out of the earth or out of the floor straight up. I'm going to get tangled in this thing. And as it comes up, it will turn around like this. Now, you see, my hands are in the same position they were down there. And that's one turn. And the distance from the position of my hands down there to the position of my hands up here is one wavelength. And it can turn either way, left-handed or right-handed. And this is the case of the right-handed or left-handed polarization, which I won't bother with tonight. Now, in any case, this wavelength is one of the important features. And in the case of light waves, it's very small, about a 50,000th of an inch for green light. And as such, that's very much smaller than the diameter of a hair. A lot of waves can go through the pupil of the eye. And so it's possible for the eye to have pretty good resolving power. Now, there's nothing about Maxwell's equations that limits it to light waves, although he put it together to discuss the conditions for light. That is, the equations are open-ended and can apply to waves longer than light waves or waves shorter than light waves. Now, in 1887, Heinrich Hertz was a young professor at Karlsruhe, and he was experimenting with a capacitor called a Leyden jar, a small inductor, and a spark gap. And by accident, he found that there seemed to be some new kind of electric action at a distance. And being a man of considerable curiosity and gumption, he quickly traced this down and found that this electric action at a distance was, in fact, electromagnetic waves as propounded and discussed by Maxwell. The difference being that the electromagnetic waves that he was encountering were about 1,000,000 times as long as light waves. So this was a beautiful confirmation of Maxwell's equations, and at the same time provided a whole new set of opportunities. Now, these waves became known as Hertzian waves. They were produced by man in a laboratory. If man could produce Hertzian waves, it seemed likely that Mother Nature could also produce Hertzian waves. This is a pretty obvious kind of a thing. It must have occurred to many people independently. Between 1890 and 1902, there were several people who attempted to locate Hertzian waves from the sun. This was a good proposition because since we get more light from the sun than all the rest of the celestial universe combined, the place to obviously look for celestial Hertzian waves would be from the sun. They all failed because their apparatus was insensitive by many orders of magnitude. Now, at that point, interest was lost in the subject. But radio communications, you see, these Hertzian waves later became known as radio waves. Well, first, in the between time, they were known as wireless waves, and then they became known as radio waves. Well, during the period that they were wireless waves, there were a lot of energetic people like Marconi and DeForest and Alexanderson and Armstrong and a host of others who developed the technology of these Hertzian wireless radio waves for the purpose of earthbound communications. It was possible to build equipments far beyond anything conceivable to Hertz and his immediate successors. And so, as time went on, the radio spectrum became more crowded, and there was a continual push to the shorter and shorter wavelengths. Now, one of the features at the longer wavelengths that limits radio communication are natural atmospherics in the Earth's atmosphere. And when the shorter waves became of economic importance and technically practical, then it was natural to believe that one of the things that should be done was learn about the atmospherics and their direction of arrival and strength at short waves. And Carl Jansky was given the job of investigating this. So, under his instructions and from his drawings, a rotating antenna was built to study the direction of arrival of shortwave atmospherics. Well, there were a few, but not many. They were only associated with local electrical storms. And a large part of the time, his equipment didn't record any terrestrial atmospherics. But it did produce some small bumps on the records. And the story is well known about how he undertook to investigate these small bumps and where they came from and what they represented, and how he was able to show that these small bumps, in fact, represented natural radio waves coming from the sidereal universe, and in particularly from the plane of the Milky Way. So I think at this point, I should show a couple of slides. Is there a pointer around here somewhere? Oh, that's it. Okay. That's good. Now, this is the well-known and famous picture of Carl Jansky and his rotating antenna. It turned around on these wheels once in 20 minutes, and the output was recorded automatically on a moving paper tape. He had a couple of years of these data. And I call to your attention about these wheels. They are wheels and front axles from Model T Ford cars, and they have pneumatic tires on them. These were plentiful in automobile junkyards in about 1930. Now, the next slide was one drawn up by me, and it shows in galactic coordinates. That is, the plane of the Milky Way is along here, and that's the North Galactic Pole, and this is the South Galactic Pole. Jansky's data. On one of his papers, he produced 24 hours worth of good, clear records, and by reducing these to galactic coordinates, we get this set of contours, and it's quite obvious that the energy has the highest intensity somewhere along the plane of the Milky Way. Now, About 1960 or 61, I was at Greenbank supervising the reconstruction of my own dish, and it was installed at the left-hand side of the front entrance. And I thought it would be appropriate if a reproduction of Jansky's antenna were installed on the right-hand side. So I contacted George Southworth, who had recently retired from the Bell Laboratories, and suggested this to him as a possible project. If he concurred, would he kindly see the powers that be with a view to doing this, which he did. And there was a very flatteringly positive response that they would be happy to do this, but there was certain things missing. The only thing they were able to find of Jansky's original antenna was the gearbox for driving it. They fortunately had all the original drawings, and by further good fortune, the man that built the original turntable array was still on their staff and had not yet retired, and he would be the man who would build the reconstruction. I later found they had some difficulty with this gentleman because he wanted to improve it, and they didn't want it improved, they wanted the way it was. But there was one further greater hazard, and that was the fact that the year was now 1961 and not 1930. And all these fine parts of Henry's Model Ts had long since departed from the automobile junkyard. And did I have any suggestion where we could get some front axles and wheels? So, living at Greenbank, I thought I might do them some good. So I put an ad in the Marlington paper requesting anyone who had remains of Model T Fords, would they please come forward, and we'd be glad to come around and pick up these remains and pay them a nominal sum for whatever they were able to produce. And lo and behold, we got an ample supply. The rims and the metal parts were in sufficiently good condition so they could be used by just sandblasting and painting. But most of the wooden parts were rather rotten, and instead of taking a chance on it, the Bell Lab decided to make new spokes to put in the wheels. There was one further catch, which seemed at first might be insurmountable, and that is, where do we get the tires and the tubes? As these cars hadn't been used for some 40 years or so. But there's another years. And these people apparently dote on Model Ts and similar contrivances. And lo and behold, there is a sufficient demand from these people to cause at least one of the major automobile tire manufacturers to produce tires and tubes suitable for Model T Fords. And we were able to get the tires and tubes for a very nominal price from Sears Roebuck. So I had to leave before it was put together. But it's out there at Greenbank, and I'm going out next week and have a look at it. In any case, in a rather peripheral way, I had some rather minor hand in getting that thing put together out there. So we now have reproductions of the two original radio telescopes. So at this point, I'm supposed to honor my obligations and talk about radio astronomy between Illinois. So you have to try to think about circumstances as they were then. And it's sort of difficult because your mind gets confused about what happened when. And it's very easy to read into things, circumstances and events which were not there. But in any case, you have to remember that as of, say, 1935, the only data available were by Jansky with his equipment. Now, he had exploited that equipment to the maximum of its ability. It was built for another purpose. And it certainly wasn't built for radio astronomy. If we're going to do radio astronomy, let us build an equipment designed for radio astronomy and not for something else. And this feature of having it scan around the horizon didn't seem to have any particular merit. We needed some kind of a device, or I needed a device which was arranged so it could make sweeps along the sky. And it should be a device which could work at a wide range of wavelengths. Now you have to remember the antenna art, as of that day, that is 1930, was mainly a question of stringing a multiplicity of wires in a wide variety of configurations over poles. And by and large, these were quite frequency sensitive. That is, they would only work at one wavelength or a very limited region of wavelengths. This is unsatisfactory because I was considering some kind of an antenna which would work at a wide range of wavelengths. And anything that involved stringing wires and then unstringing them, restringing them, and all that was not a practical proposition. So the device had to be achromatic and capable of changing from one wavelength to another rapidly with the minimum amount of effort and complications. We could use the Earth, the rotation of the Earth, for sweeping along lines of constant declination. So it ended up by feeling that the thing to do was to build a meridian transit instrument. This is an instrument which looked in any direction along a plane from the north through the zenith to the south. Setting it at the appropriate declination angle or elevation, then leaving it rest there until the Earth had turned once would give a sweep along that line of declination. Then by building up making many sweeps at many different declinations and taking all these data and building them up, it would be possible to get a picture of where the radio waves came from. Also, Jansky's antenna had a very poor resolution. That is, it was about 30 degrees wide in horizontal and about 35 or 40 degrees wide in the vertical. This gave a very poor idea of where the radiations came from. So the new antenna should have high resolution. This meant it should have many wavelengths aperture. Now nobody had any idea what the intensity of these celestial radio waves was versus frequency. And so, since the ignorance is profound, you make a fresh air guess. And I guessed, probably hoped or wished, that the intensity would rise as the frequency rose. So this told you two things. It told me that the frequency should be high because for any given aperture, I'd get a higher resolution. The frequency should be high because presumably I would have more of a signal to deal with. This meant I should try to build the largest kind of a dish practical within the realms of my financial capability and the location. Now, in a measure, it has to be remembered that I was in a very favorable position. I was working in the radio industry and had been for some years prior to that. I graduated from electrical engineering school. I had written to Jansky and inquired as to whether or not they were going to do some more of these experiments. He replied that they were not, and that my hope of joining him and doing experiments there, of course, closed. I wrote to Harlow Shapley. He was quite aware of Jansky's observations, but Harvard University was not going to do anything. Partly, apparently, they were financially overextended, and partly he seemed to feel that this was outside their realm of competence. I talked to Otto Struve a couple times at Yerkes on this same subject. And he took a rather benign view that this kind of experiment should be done, But in that day, anything as complicated as the photocell in a DC amplifier was considered to be black magic. So things like vacuum tubes and tuned circuits and all that were out of their realm of working. I wrote to a couple others and got a uniformly empty response. So here was the situation where a first-class fundamental discovery had been made and nobody was going to do anything. So it seemed that all I had to do was do something new and different and keep my eyes open, and how could I fail? It was practically surefire. At least that's the way it looked. So this dish was designed, and it was constructed on the basis of what materials were available. And the longest 4x2s available were 20 feet long. So this fixed one of the dimensions of the dish. Square 20 feet on a side is about 28 feet on a diagonal, and the dish can extend a foot or two beyond that, so that meant the dish was going to be a little over 30 feet in diameter. And then I canvassed the people who sold sheet iron to find out what sizes of sheet iron came in, and I was pleased to find that I could buy sheet iron that was a suitable size, and they would be glad to cut it in sections of pi at practically no extra cost. Now you have to remember, this was in the 30s when people were anxious to work. And they did this according to my instructions and delivered it out there at prices which today wouldn't have paid the freight. So I decided the thing was to do was to go ahead, and the smart thing was to build a model to see what this looked like. So I had plenty of room in the side yard, and there was a good clear horizon to the south, and I decided to, and prior to that, let's have the next slide, please. This is a model of the framework that was constructed before the dish was built. I'm sort of a pack rat, and I save everything. And that model was about a 1936 model, and this black piece in the foreground is 6 inches long, to give you some idea of the scale. And the next slide shows it tipped over to the side. This was just to satisfy myself that the structure would be solid and rigid, and it was. So that then was turned into a full-size antenna. Mainly by dint of my own efforts. That is, I put up the money and did most of the work. I hired some labor helping me dig holes and mix cement and that kind of thing, but most all of it was put together personally by me. That is, I cut all the timbers and drilled all the holes, and I had the local blacksmith cut. See, it's made out of timbers fastened together at the junctions with steel gusset plates and bolts. So all these gusset plates had to be cut and drilled, and there was, I don't know how many thousand holes in those. And that was done by the local blacksmith. Well, while all this was going on, or prior to this was going on, I tried to see what could be done for the shortest wavelength possible. As I mentioned to you, that the resolution would increase, that is, the ability to distinguish one direction from another would increase as a frequency increase. So the idea was to go to the highest possible frequency or the shortest possible wavelength. And in that day, around 10 centimeters was the shortest wavelength which could be achieved. And as I say, I was in a favorable position working in the radio industry, as I had access to the best test equipment that was available today, And we had some pretty good salesmen that came through there who were anxious to sell their product instead of tell you they didn't have anything to sell. And they had good contacts with the factory. And I found out that the RCA man could get me a small magnetron, which I shelled out about a week's pay for. And this magnetron I still have. And it worked from, about 7 to 11 centimeters wavelength, something less than 2 to 1. It produced enough energy to light a small bulb like used in an electric flashlight. And all the magnets and coils and so on were wound and made courtesy of the Stuart Warner Corporation. So, again, you see I was in a favorable position. Now, the next slide shows some of this microwave test equipment. That's the yoke of the magnet, and these are the coils, and the magnetron is done inside there, and this is a lesser wire coming out, and there's a shorting bar which acts as an antenna on the end of this, and over here is the receiver, which consists of a cylinder with, in this case, a horn on the end, and the crystal detector is inside the cylinder along with a small dipole, and there's a tuning plunger at the back end you can shove in and out. And the output of this can go either to a DC meter, or an DC amplifier, or this magnetron could be modulated with, say, a tone or even with a voice, and the audible output heard on headphones. So the purpose of this was to learn something about the tuning of microwave cavities and what happens when you put on different size horns. Now, this array of horns shown here are all the same aperture. I think there's a 2 to 1 aperture. This aperture is twice as big as the aperture on this cylinder, but have different tapers. And this produces a different configuration. And by turning this affair on the pivot, which is directly underneath the aperture here, it was possible to determine what the acceptance pattern of this thing was. Now, that was pretty important because you had to have an acceptance pattern which would look at the dish and not look much outside the dish, but it had to cover the dish pretty well. In other words, this had to be tailored to fit the size of the dish. And all this Gil Geiger down here is just for providing the necessary voltages and currents to this magnetron. And the next slide shows some pretty damn poor slide. This was taken with that previous picture were old pictures. This is a current picture taken about 2 months ago of the apparatuses that exist today. And this is the magnetron. And there's the antenna across the ends of it. And this is my wave meter. And it's called a Lesher wire, which is nothing but a hairpin loop. And there's a threaded arrangement here which allows the loop to be carefully moved, shortened or lengthened. And you can determine your wavelength by that. It'll be a half wavelength long. This is another one, but it has an electric lamp bulb on the end. And this is that cavity you saw. And this is another larger cavity, but it has a flat end on it, and you can't see it because the picture's so poor, but there's a hole in this, an iris, and I could change the ends of this to have different size iris. Now, this was my signal generator, and I needed a detector, which in the case was a crystal, and they're inside of these things. I pretty much made up those crystals myself because they had to have mountings that would have suitable physical dimensions for 10 centimeter wavelength. And then I hoped to build a fancier receiver because we were building super heterodyne receivers. regularly at the radio companies, and they had a certain amount of merit in that you get a lot of gain out of them. But in 1935, there wasn't anything suitable for a local oscillator. The klystron tube hadn't yet been invented, and the only oscillator available was this thing. And if you try to use that, it has a terrific shot noise in it, just hopeless. And so there were some articles about a Barkhausen tube. And so now a Barkhausen tube is a triode, but it's arranged so that the grid is positive and the plate is negative. And the electron transit time is invoked to make the thing oscillate. And this was specially built Barkhausen tube with a single grid and two plates on the opposite sides of the Lesher wires. And it was used for a detector. But the thing is emission limited, and as such it has tremendous shot noise. Again, it was useless. So that was another failure. And then I thought, well, maybe I could build a small diode. And so this is a small diode. There's a small tungsten filament across there, and there's a tungsten anode sticks through the end of it. And the idea was to have a very small gap. It's only a few thousandths gap between this filament and the tungsten anode. And it worked, but again, the thing was emission limited, and it had tremendous shot noise in it. The sensitivity was very poor compared to crystal. I used a lot of different kind of crystals, and most of them were pretty erratic in that you had difficulty finding a sensitive point. But I stumbled accidentally across a piece of material which looked like amber, very clear amber, which I later found out to be some kind of a natural zinc sulfide called sphalerite. And the surface of that must be impervious to the action of the atmosphere, because no matter where I touched the whisker, it had good sensitivity. It was really a remarkable thing. So I ended up using these sphalerite crystal detectors and a high-gain audio amplifier. And they were put on the dish, and a lot of time was expended trying to find something with it. And I tried the sun and the moon and the planets and the Milky Way and what have you, and I was unable to find anything. It was a complete failure. And it is possible, though, to get some idea of signal the sensitivity of the system, because on the previous slide you saw I had that magnetron, and that crystal could be calibrated in at the radio company using their 1,000-cycle oscillator, and you could get an idea of the sensitivity of the crystal. That is, I could read down to a fraction of a millivolt with a high-gain audio amplifier. And then you make an assumption and say the crystal works at 10 centimeters as well as it does at 1,000 cycles. But there's probably some truth in this. And from that, I could make some kind of a guess as to what the sensitivity of the system is. And it became very clear that the proposition that the intensity rose with frequency was a wrong assumption. It may have risen with frequency, but it certainly didn't rise at any high power of the frequency. See, black body radiation rises as the square of the frequency. So if this demonstrated anything, it demonstrated that these radio waves that Jansky had discovered were not black body radiation of any form, because they certainly weren't rising as a square, the intensity is the square of the frequency. So all that was for nothing, and that took a better part of a year. Well, this was mostly all done before the dish was built, to try to get some grasp or some hold on what the technology would be. The dish was built, and this was tried, as I explained. So the next thing was to try some lower frequency where the sensitivity achieved could be much better. And so I decided to fall back on vacuum tubes. And about this time, RCA brought out acorn tubes, which literally were the size of a small acorn. And the highest, and build a regenerative oscillator and then set the thing just below the oscillation point. And this would oscillate at a wavelength of about 33 centimeters. And the next slide shows some of that gear. This is the antenna inside a paint can. This paint can is about 10 inches in diameter or so, a little over a foot long, maybe 15 inches long. That's this resonator that I showed you on the bench, only it's been scaled up from 10 centimeters to 33 centimeters. And this is not at all clear, but that's the detector rigging there with some acorn tubes in the other side. This picture is taken from the back of that. And the next slide shows it mounted on top of the dish. This bottom cylinder is the resonator with the aperture in the bottom, and the top half of it, or top third of it, is just a can that holds the receiver detector. And the output of that comes down a cable, which also brings up the electricity to run it. And the amplifier is at the bottom. And I went through this whole business again of looking for 33 centimeter waves from Vega and Antares and the Moon and Venus and what have you, and turned up nothing. But now we're getting a bit closer, and the sensitivity had gone up by a couple orders of magnitude. So it seemed the thing to do was to persist. I have the reputation for being a stubborn Dutchman. In any case, about this time, some other acorn tubes came out, which were pentodes. And it was possible to build a really good amplifier. Now, you see, I've been gaining experience in the radio industry, and a super heterodyne is invented by Armstrong. It has certain characteristics which are desirable from a communication point of view, but they aren't necessarily desirable for this purpose. The technology of that day, you needed a high-gain RF amplifier in front of the mixer on the superhead to cut down the noise in the mixer. And it was very evident at this stage of the game that I had to build a receiver that had the lowest possible internal noise. And so the crux of the thing was not the back end of this electronic apparatus, but the front end, namely the RF stage. And it had to be a good one, the best one possible. And what happened after that was more or less immaterial. So I decided to build the thing just tuned radio frequency. You have to remember that all channels were empty in that day. There was none of these frequencies were used at all. So it didn't make much difference what channel I chose. And now we come to grasp with another practical problem. At a longer wavelength, we're going to have to build a big resonator. And how big a resonator can be built economically? And this again depends on the size of the material. And it turned out that 16th-inch aluminum sheet came in standard sizes, 6 feet long, 6 feet wide, and 12 feet long. So you could roll a single sheet into a cylinder approximately 4 feet in diameter and 6 feet long. And so I approached the Aluminum Company of America. Would they make me a drum with an assortment of removable apertures with different size holes in them? They would. Thinking about things in today's context, it seems just incredible, but these people put themselves out to do what the customer wanted. It was just incredible. It was still in the day when the customer is always right, instead of the customer be damned. Well, they built me this drum, and that pretty much fixed the frequency, which was going to have to be something less than 2 meters wavelength. So I now had a better grasp on matters, and the next slide shows some of the equipment. Oh, this one fits in between. This is the turning mechanism for the dish. This circle, I think, is about 22 feet in diameter, which is the track it runs on. And there's some wheels that I bought in Chicago. And again, I got those for what's about like 10 cents on the dollar now. Then this is a shaft, and this piece in here behind this plank is the rear axle of a Model T Ford truck. So Jansky used the front axles of Model Ts, and I used the rear axles. So old Henry had, you know, quite a hand in this. And these universal joints came off of Model Ts, and that spline goes on where the transmission shaft, and we cut the transmission shaft off and put on a crank. That's a crank. It doesn't show very well. It was possible to turn this thing by means of that crank, and then it was clamped and positioned by some clamps which don't show here very well. There's one of them hanging down behind that post. Well, in any case, the next slide shows some of the next electronic apparatus. This is sort of an innovative design in that you have to remember the technology of that day was coils and capacitors. But when you get to a couple of meters wavelength, even with acorn tubes, the coils get to be minuscule. And so the losses in them also are pretty high, and they're hard to handle. And so these are cylinders with another cylinder inside called a coaxial resonator. And the whole thing is brazed together by my blacksmith. See, this is all copper. It's brazed together at the joints. And this all top piece was all brazed in there. And the whole thing is one solid lump, you might say, with the vacuum tubes fitted up in the top. And the next slide shows, I think, the bottom of this thing. No, this shows the top. You can see these resonators. There's these pipes. And then the inside pipe creates a short section of coaxial line. And I forget, I think, yeah, let's see now. That's the output. Comes in here and works its way around. There's the first tube, comes through here, the second tube, third tube, fourth tube, fifth tube, 5 stages, and that's the diode detector on the output. These are nothing but isolating chokes in the heater leads. And this thing had a lot of gain. And the next slide shows the bottom of it. This is merely where the DC voltages feed up through the center pipe to the vacuum tubes at the top. This is where the energy is picked up from the antenna in the drum. The gain on this thing was on the order of 90 dB, and a bandwidth a couple of 100 kilocycles, a couple tenths of a megacycle. And I think the next slide shows, this is an old picture. This is the control box, and these 2 meters here merely read DC voltages, and the output is read on that meter there, which isn't particularly legible. And I don't remember what those things do. I think they had some more voltage control. So this is just a picture of the amplifier sitting beside its control box. And the next slide shows the same thing taken today. For some unknown reason, that rheostat was taken off, but I know where it is, so it could be put back on. I saw it not long ago. I apologize for the poor quality of these slides. I'm glad I had some made of the old original pictures. Anyhow, you can see the markings on this meter. It's a microammeter, 0 to 200 microamperes. And I'll explain that a little later. And the next slide shows the inside of this box. This box was last used in 1939. And there are 1, 2, 3, 4 of the original dry cells in there. And when I tested them, they had between 9/10 and 1 3/10 volts in them. Now, I think that's a good recommendation. I didn't check their internal resistance, which obviously is very high. And there was an audio amplifier in here so I could listen. Now this was a very important thing, because if you have a lot of spikes and bumps on the records, just the spikes and bumps, unless you know what they have some meaning. And if you can listen in, the audible sounds associated with the discontinuities in the record give you quite an insight as to what's happening. That is the equipment difficulty, or is it some kind of man-made interference? And if so, what kind, and where's it coming from, and such like. Now, I think the next slide shows, yes, this is my signal generator, believe it or not. There's a couple of Type 76 tubes which would operate at about 2 meters wavelength when had the bases taken off and this rigging and stuff connected up. And it's not exactly a signal generator in the sense that it doesn't have any calibrated output, and it's not tunable. It's adjustable in frequency. By adjusting these bars, you can change the frequency. So you set this using my wave meter, which I'll show you, to a desired wavelength, and then the output of this is picked up here and goes over a coaxial cable and is injected into the top of the receiver. And you can find the stage gain by, say, putting this on maybe, say, the 5th stage and setting it for some low output on the output meter of that control box. Then you move it without changing anything else. You move it up to the 4th stage, and maybe the output meter goes up, say, 12 times, in which case the stage gain is then 12. And you just keep working it along like that, and you can find out how much gain the entire system has. The thing had great merit in that, as I pointed out, you've got to have a receiver which has the lowest possible internal noise. And this will be achieved if the internal noise is mainly in the first tune circuit. So you should be able to detune or short that first tune circuit and get rid of most all the noise in the set. And you could. That is, this receiver was working at a wavelength less than 2 meters, had a performance equal to or better than the sets that we were making for the broadcast industry. So this was quite reassuring. And now I had a pretty quantitative kind of receiver. I could measure its sensitivity in sort of an indirect manner, and I knew it was good. So then another set of measurements were started, and I think the next slide shows some of that. This is my wave meter from here to there, and that's that 6-inch marker, and I could lengthen or shorten it by turning a nut down here. And this is the antenna from there across there, and it was mounted inside the drum. So another set of measurements were started, and I think the next slide gives some idea. This is the inside of the drum. This, you can see the antenna wire if you look carefully. It runs up like this. And these are the pieces of wood that it's mounted on. And this is the mounting on the end of the drum where the receiver goes. And this drum is about 4 feet in diameter. So let's see what the next slide is. I'm not following my list here. I should know better. Yes, this is the picture of the dish with that 4-foot drum, 6 feet long, mounted up there. And you can see the opening, the iris at the bottom. In other words, this is just a scaled up version of those things I showed you on the bench at taking a 10 centimeters wavelength. And the 20-foot length that determines the size of this thing is the distance from there down to there. And you see then it'll be 28 feet from there to the opposite corner. This sticks out a couple of feet, and so that makes about a 31.5-foot dish. And I built it with an opening in the center purposely because in that day I had great ideas that it could be used as centimeter wavelengths. And the purpose was that it could be made into a Cassegrainian job with the equipment down here at the bottom where you could get at it and have a secondary mirror at the top. That never transpired. But the dish is quite good. That is, when it's vertical, pointing up, which is the way it was constructed, there was this flat plane around there, and that was leveled flat to about plus or minus a 16th of an inch. And then these sort of stays that run up and down there, they were all accurately measured. So probably the RMS accuracy of that's about plus or minus an eighth of an inch. And the next slide is a poor slide because the person that took this had a heavy hand and jiggled the camera. But that's me in front of the end of the drum. Now, the next slide is the thing that I've been fussing around to get for about the past several years. You remember that meter I showed you at the right-hand side? Well, that was the output meter. And the biases, the DC voltages were so arranged that if there was an increase in signal, the pointer on the meter went down. Now, this may seem odd, but it really doesn't make any difference whether a pointer goes up or down, just so you know which is which. Now, this is not maybe the very first record that was successful, but one of the first records. I don't know if there's a date on this thing or not. In any case, it was done by sitting there all night and making minute-by-minute entries in a logbook as to the reading on that right-hand meter. And at 1 a.m., it had previously warmed up mostly, but at 1 a.m. it was still warming up, so there was a slight rise for another 30 or 40 minutes. And then it achieved what amounted to a stable baseline condition for about 15 minutes. At this point, the plane of the Milky Way came into the aperture, into the receiving cone of the antenna, and I began to get celestial radio waves at the wavelength of 2 meters, as shown by the fact that the numbers are decreasing. And at this point is where the plane of the Milky Way went by, and then the numbers increased again minute by minute for approximately an hour, and finally stabilized and continued along with a very slight drift upward. So the baseline drift starts right about there and continues uniformly to the end of the observation. This doesn't look like much, but after several years of fussing around and building all that equipment, this was quite an achievement, at least as far as I was concerned. And it gave me confidence. That is, I had now been able to confirm Jansky's observations at a wavelength of 2 meters, where he had operated a wavelength of 15 meters. And as you can see, the results are good. That is, it's got a high signal-to-noise ratio. Even these visual numbers recorded in a notebook and later plotted give a very clear demonstration that the radiation is coming from the plane of the Milky Way. And on top of that, I was able to put some numbers on it. That is, to find out what the intensity is. Not accurate numbers, but give me some idea. It's always better to be able to put numbers on some phenomena that you can see than merely say the phenomena is below some arbitrary limit of detection. So you have to remember, I was working in the daytime and I was trying to stay awake in the nighttime while all this was being done, and that's not good for one's health. So with this much results in hand, I decided that there was no point to skimping, and I might as well do a good job. So at this point, well, this was taken during the spring of 1939. At this point, I decided the thing to do was to build a really good receiver. And I had a better grasp on matters now, and it was evident that the receiver should have a wide bandwidth and should be more stable. This thing had some mechanical difficulties in that if the sun shone on it, it distorted the thing slightly, and some of those sharply tuned circuits went out of tune, and the gain would rise and fall. But of course, that wasn't bothersome at night. But in any case, it should have a wide bandwidth and be more stable, and preferably increase sensitivity. So the next receiver was built. The next slide, please. Which has some similarities to the previous one, except instead of being single-tuned circuits, these are double-tuned circuits. That is, there's one resonator to the center and another resonator from the top. There's a partition in the middle and a coupling stub. So what we have here is a double-tuned circuit using pieces of concentric line as the tuning elements. And half the amplifier stages are at the top and half the amplifier stages are at the bottom. So it goes around in a zigzag fashion, starting up there, across there, and down here, across there, up here, and so on. And wherever you see a partition like that, there's a tube in. There's no tube in there, for instance. There's no tube in there. So this was constructed, but before it was well, all right, let's take a look at the next slide. I think this shows one of the ends of it. Yes, it does. And there's in this case, there's a very fine wire goes down the center instead of that inside pipe. And that's part of the improvement that it's possible to lower the capacity and increase the bandwidth. This had a bandwidth of about 6 megacycles. And again, a gain of about 90 dB. Now, if you go out and just put everything lined up beautifully. Now, the next slide shows the inside of this signal generator, which I'm rather proud of. This is the oscillator. All you have to do is know the distance that the pickup coil is going up and down the pipe, and you have your attenuator automatically calibrated. And it did a very good job. It was a good quantitative piece of engineering. And the next slide, oh yes, this is the new mounting for the new receiver on the end of the drum. And at this point, I had to change the antennas because the old antennas were too sharply resonant. So the iris was taken off, and the drum had full aperture, and a pair of cones were put inside. And this broadbanded it out enough so that the whole system was functional over a 6 megacycle bandwidth, which is about 4%. And the next slide shows some of the results. And these are drift curves. If you look at them critically, you'll find that there's hardly any zero drift to the baseline. That baseline is about one small division above the big one, and it's exactly the same over there. And these curves, you can see it also had a high signal-to-noise ratio. The equipment was not anywhere near sensitivity limited. That it was definitely resolution limited. And the last drift curve here is taken on a night when we had a local electrical storm. But even the local electrical storm didn't blot out the results. So this thing was run for the better part of a year until the sky was covered. And see what's coming up next. And the next slide shows the results. This is the winter Milky Way with the Sagittarius region toward the center. And this is the Cygnus region. Aquila is in here, the Cassiopeia region. And the phenomena got below the sensitivity limit of the equipment in Perseus. And the next slide shows the summer Milky Way, or the winter Milky Way, I guess. Well, I forget. Anyhow, this is Perseus up in there. It runs down through Taurus to Pappus. And it definitely shows that the radio waves are associated with the Milky Way, and further that there's an assortment of minor maxima in it, with the major maxima in the direction of the center and the weakest signal in the direction of the periphery. So in some fashion, these radio waves are coming from the Milky Way. Now, during the daytime, there was a vast amount of ignition disturbance from automobiles passing by. And so not much attempt was made to do daytime observations. And why I didn't make the observations sooner, I don't know, except that it didn't look hopeful. Because if you take the sun at 6,000 degrees and compute how many radio waves you're going to get out of them at 2 meters wavelength, it appeared to be far below what the capability of this equipment was going to measure. In any case, it was 1943, I think, early 43, when I gave it a try. And at that time, I was making some observations on the peripheral part of the Milky Way, and the gain was set up pretty high. And so I just left the gain where it was and set the declination for the sun of that day and went away. Came back that night, and lo and behold, the pen had gone off scale for about 3/4 of an hour. And it seemed as though all this tremendous radiation was coming from the sun. So I stopped the gain back by about 20 dB and tried it again. And again, the pen went off scale, but didn't go off scale for so long. And the third day, I stopped the gain back another 10 dB, and this time, the pen stayed on scale. So there were radio waves from the sun, and they were of tremendous strength. That is, the strength of them was comparable with the strength at the center of the Milky Way. This was dumbfounding. If I'd had any idea they were going to be that strong, I could have detected them several years earlier with much more primitive equipment. But it's one of these cases where a little education is a bad thing, because, see, I had education, and education told me that the sun was a black body radiator at 6,000 degrees. And at 6,000 degrees, the prediction was the receiver wouldn't detect it. If you work this thing backwards, which I didn't at the time, it turns out that the sun has a radiation temperature of around 1,000,000 degrees. In any case, the next slide shows the sun going through the Milky Way during the winter solstice. And this one is taken on the dates the 14th of November, 1943. And there's the plane of the Milky Way, and there's the sun. You see they're nearly the same amplitude. And all that roughness on there is automobile ignition noise. A week later, you see all these objects move eastward through the sky. The Milky Way, of course, is fixed, but the sun, the moon, the planets move eastward through the sky. And so they appear earlier. And there's the sun now. See, it's gotten closer to the plane of the Milky Way. And another week goes by, and the sun is still closer. And then about 3 weeks go by, and they're practically coincident. There's the plane of the Milky Way, and there's the sun. And the next slide continues this series. And now we are, I think, on the 1st of January here somewhere. Oh, Christmas Day. And they have changed. There's, you see, the sun is on the left, and the plane of the Milky Way is on the right. And on the 1st of January, a week later, the two are beginning to separate. There's enough resolution now to see that they are two distinct ones. And 2 weeks later, they're definitely apart. And by the end of the month, the 30th of January, 1944, they are definitely far apart. So there you have an example of the sun crossing through the plane of the Milky Way. There's one celestial object moving in relation to another. So that was my contribution as far as the sun was concerned. And if you notice, during that period, the sun always had about the same intensity, at least to the extent you could measure its accuracy within all that automobile ignition disturbance. So the equipment was pretty well worked out now. That is, nothing much more could be found at 160 megacycles with this equipment. There didn't seem to be any point to trying to build a more sensitive receiver. And either I could discontinue the whole thing or try for something better. And so now, having had this much success and gotten a pretty firm grasp on the intensity of the phenomena and how the whole thing worked and what to look for, it seemed the thing to do was to again try for a higher frequency. So I decided that the least improvement worth anything was 2 to 1, and a 3 to 1 it would be better. So if I could get an equipment to operate at 60 centimeters wavelength instead of 2 meters, the resolution would be improved by a factor of 3. And I could now make an extrapolation downward and find out what sensitivity necessary would likely be. Using Jansky's data at 15 meters, my own data at 2 meters, what would necessary sensitivity be at 0.6 of a meter? It did not look hopeful. But since the recent past had demonstrated that progress was possible, it might be appropriate to give it a whirl anyhow. So I got these acorn tubes, incidentally, would be useless at 60 centimeters wavelength. So I got some valves that had a much higher transconductance. They were called electron multiplier tubes with the same electrode capacitances, and the electron multiplier, they had about 10 times the transconductance or more, or 1,200 to 50,000. Yeah, about 30 times the transconductance. So I bought some of those and had a lot of machine work done, and the next slide shows some of that. This is a 60 centimeter amplifier using these electron multiplier tubes. And there's one of them. It's like a big acorn tube with a lot of wires coming out of the periphery. And this is the 6-inch scale. And there's one of these in each one of these boxes. One in that box, one in this box, one in that box, one in that box. And these are tuned circuits in between. And these things really could amplify. This thing had about a 20 megacycle bandwidth and about a 30 dB gain. So 4 stages did 20 megacycle bandwidth and 120 dB gain. And that's no mean feat. And then the detector was balanced, so I had 2 diodes in here. And this looked like it would do the trick. At least it had plenty of gain. It also had a lot of noise. Because the shot noise in these electron multipliers was tremendous. So the effective sensitivity was very low. And I used that for quite a while. Well, not quite a while. A few weeks or a month, maybe more. And I couldn't find anything. That is, the phenomenon was there. It was below the capability of this thing. Except on one day. On one day, at the right place, there was a bump, which should correspond with the sun. But it was only that one day. It didn't occur any other day. And at the time, I wrote it off as one of the vagaries of the equipment. But it was a smooth bump. That is, it wasn't a bump like an automobile ignition disturbance or some other man-made thing. In retrospect, what probably was happening was I had accidentally stumbled on a day when the sun was radiating in an enhanced fashion, but I didn't know it. And these enhanced fashions only last for matters of hours. And so it was just one of those things. In any case, after all that effort, I still, again, had nothing. So about this time, this was, I think, about 1945, I had access to some lighthouse tubes. These are high-frequency triodes. And the next slide shows equipment's built for that. Couldn't get as much gain out of them, but there's a lot of stages here. I think there's about 5 or 6 stages. Well, there's one behind each one of these openings. 1, 2, 3, 4, 5, 6. There's 6 stages. And that was a pretty stable amplifier. Had quite a lot of gain and about a 6 or 8 megacycle bandwidth. And with that, the next slide shows it from a different angle. And the antenna goes into there, connects into there. And the next slide, I think, shows it on top of the dish. The receiver is in that cylinder. And in the meantime, I had done a lot of experiments on antennas to find out what was a good configuration. And this idea of putting the antenna inside of an enclosure seemed to be quite valuable because it cut out primary pickup from all directions except the dish. And that automobile ignition noise was just leaking in along the edge of the dish. It wasn't leaking in from behind or anywhere like that. So that was continued, and I decided to form it into a cone. That original scheme, time's running on, that original scheme consisted of that cylinder acting like an ellipse where the real aperture was at the iris, and then the cylinder had a second focal point back inside where the antenna was. And I decided to dispense with that and just have one focal point at the antenna, right at the focal point of the dish, and with the cones in there, it would radiate with a cylindrical field. So the next slide shows some of the results. And as expected, these bumps in the curve are very faint compared to what they were to 2 meters wavelength, but they're there, and they're reproducible. And again, you notice the stability of the baseline. In view of things that are even happening today, I'm rather proud of the stability of that equipment. Now, let's take another. Yes, these are the drift curves, and then a lot of data was taken, and these then showed the contour maps taken again on the next slide. And you see the Milky Way is narrower, it's fainter, but there's a lot more detail in it because I've got 3 times as much resolution. There's the center of the Milky Way. There's the bump in Aquila. The Cygnus region is divided into 2 places, and there's a minimum in there. I didn't have a chance to get the whole thing, but the Cassiopeia region also has a maximum. So it repeats. And the other Milky Way, the other branch, next slide, is very greatly contracted. Perseus is up there. This is the Crab Nebula, and I forget what these are. I think the Loop Nebula, and I can't find anything down here. So the whole thing repeats with more detail. Now, another thing happened about this time. See, in the meantime, I was still working in the city, and this thing was running automatically at night, and then in the morning I'd get out there and shift it until it pointed at a declination where the sun would drift through it in the daytime, come back at night, reset everything, check everything, make sure it was recalibrated, and then reset it for another night's run. So the thing ran most all the time, day and night. And didn't have much trouble, fortunately. Now, the next slide shows the sun at 60 centimeters wavelength. Now this, see, we still get automobile ignition noise, but it isn't as severe. The automobiles weren't as loud at 60 centimeters they were at 2 meters. And furthermore, the sun is stronger, relatively speaking, and we got these drift curves. They're very much clearer and very much higher, apparently, and also notice how much narrower because of the increased resolution. And this is a typical drift curve. And I did notice that they changed from day to day. Some days they'd be higher and some days a little lower, but they were always usually smooth curves like this. However, occasionally I get one like this, which looked as though there was severe automobile ignition disturbance sparking at the time the sun went by. And it was most mystifying. Why should the automobiles choose to act up just when the sun went by? Why weren't all these spikes and stuff occasionally out here somewhere, see? And underneath this envelope, you can see the same kind of thing is there. Well, this happened one time when I was home on a weekend. And it was quickly unraveled by pointing the telescope away and then back toward the sun. And it now became apparent that these, in fact, were solar transients that were being produced by some kind of activity in the atmosphere of the sun. And they would come and go in an irregular manner. So there is solar transients. These were entirely absent in 1943 and 1944 when I was working at 2 meters wavelength. See, this is now October 1946. Well, that was about the end of that. And along about this time, or a little before, see, this is October 46. Well, I think it was toward the end of 45. Immediately after the war, anyhow, Van der Hulst showed up, and he visited Yerkes Observatory, and they brought him down to see my rigging, and he wanted to know what the possibilities of making a receiver that would work at 21 centimeters. Yes, it was earlier than this, because at that time, this receiver hadn't even been built. I was still struggling around with that one that wasn't any good. And I didn't have much enthusiasm for it because I hadn't gotten any results at that time at 60 centimeters, and trying to think of something to work at 20 centimeters just didn't seem very reasonable. So I asked him where these radio waves were going to come from, and he gave me the obvious answer. He thought they'd probably come from the center of the Milky Way. And I asked him if they would be an emission line or if they'd be an absorption line, and he wasn't real sure. The idea being that if they were an emission line, it could be possible to fish up the background and then put a tuned circuit on it, and the emission line would then be above the background and be easier to find. Well, in any case, by the time this was going, see, I was doing apparatus construction at the same time this was running, because once an affair like this got going, there was nothing more you could do to it except let it run and collect data. So I thought the thing to do was try some apparatus construction for 21 centimeters. And there wasn't anything to be had. So the first thing to do was to build a signal generator. And the next slide shows that. Oh, pardon me. This is barely the 2-meter data and the 0.6 of a meter data in galactic coordinates with the plane of the Milky Way, horizontal, and galactic latitude up and down. You can see how they have similarity, but in detail rather different. And the next slide shows the 21 centimeter signal generator. This is my 21 centimeter wave meter. It's the same kind of a thing, only to a suitable scale. And this is a frequency control dial. This is the attenuator dial. This is the output meter, reference level. And the next slide shows the inside of it. It's the same kind of a thing with an oscillator and a pipe-type attenuator with the pickup coils running in and out. This is the lighthouse tube, which is used in the oscillator. This is an IMAC diode for determining the reference level, which is taken at 1 volt. And the next slide shows some of the apparatus. Now, lighthouse tubes weren't suitable. But about this time, Sylvania, I think, brought this thing out called a rocket tube. And see, these are some more resonators. And they're all very small, because now we're only at 20 centimeters wavelength. We're now practically back to where I started at 10 centimeters. Except the technology is improved by many orders of magnitude. And one tuned circuit is from there to there. In other words, there's 1, 2, 3 stages here. And the whole thing was designed for, I think, 6 stages. These produced 15 dB gain on a 13 dB bandwidth. And there were 2 detectors. This is one of them using this IMAC diode, and not very successful. And then some German wartime equipment became available. And this is a double diode out of a German radar. And that was used quite successfully in there. It was over 20 dB gain in that last stage. And this is that 6-inch measuring scale, so you can see how small all this stuff has become. And the next slide shows the antennas. This was to be a cone. It was never finished. And this is the horn antenna. And the first stage connected down to the base of the horn. See, this gets narrower and narrower. And then there's the pickup antenna really is part of the tube. It's the proper point back in there. And let's see. Oh, yes. Now, this would be all right for the continuum, but if you're going to find the hydrogen line, you had to get some selectivity into this system. And you see, what a person does depends on his thinking, and his thinking is determined by his past experience. In retrospect, this should have been built as a superheterodyne to get the selectivity and the tuning. But for some reason or other, I got started this way, and so I kept at it. And so the selectivity now had to be injected into this system in a different manner. And this was done by a very high Q circuit known as an echo box. And I think the magnetics, electromagnetics inside this echo box are rather similar to the spiral wave that goes down one of these waveguides in a mode that has low loss. In any case, the next picture shows this echo box. You see, it's about 1 foot in diameter and about 10 inches deep, and there's a plate inside which can move up and down, changing the length of the box. And you do that with this knob. And this box has a Q of about 50,000. So 1,420 megacycles divided by 50,000 gives 30 kilocycles bandwidth. It was possible to measure this with that signal generator. It really did. This was some kind of surplus. I can't seem to remember where this thing came from, but it was part of some test equipment used by the military. In what capacity, I haven't any idea. But anyhow, it seemed suitable for this. Well, in any case, it was never finished. Everything was moved to the Bureau Standards when I went there. And at this point, there are probably people who wonder what I looked like back in 1938 or 1939 when this kind of stuff was going on. And so I was somewhat surprised and perhaps dumbfounded to see the last slide. Well, in any case, that's the history of radio astronomy in Wheaton, Illinois. And it's one of these one-shot deals that you don't do over again. But it was good sport at the time, so I thank you.